I turn it over to you, Parag.
Thanks very much, Brent. All right, great. Welcome everybody to the webinar. Great to have you guys, and I love taking this opportunity to even share some of the benefits of our classes and some of the basics of this very, very important foundational knowledge. So the topics today, the agenda today is why is it so important, first of all. Then we'll talk about the basics of the TCP/IP protocol suite. We'll talk about the basics of specific protocols like IP, TCP, and UDP, and other core protocols as well, basics of routing, TCP/IP, and subnetting. Just a brief synopsis of IPv6, and then we'll move it to Q&A. So first of all, why is this so important? Why is knowing TCP/IP so important? And of course, the biggest reason is it's universally used. That is the protocol we use in a vast majority of our networks today, including not only at work but at home too, right? For all of our connectivity to the internet, the Wi-Fi networks that we have at home, all use TCP/IP. Without this knowledge, we can't really design, operate, or manage our networks, or even troubleshoot. So this is stuff that can be helpful, not only for work but even at home, right? You'd be a champ amongst your friends and family if you can help troubleshoot networks, make things work, right? And so that's the beauty of this foundational knowledge. What is TCP/IP? Well, it's a suite of protocols, suite being the collection, and protocol being a standardized set of rules. Notice right now we're using a standardized set of rules, right? We call it English, right? If someone who doesn't understand English enters this webinar, they won't know what we're talking about, or they'll think the person on top of the panelist list is making a lot of noise. That's what it is. So protocol is a standardized set of rules. There are hundreds of protocols within the suite TCP/IP, right? Within the TCP/IP suite. Some are considered core, though. They are essential. They are the most important ones. And here's just a short list of some of them, right? There's not a complete list, but some of the main ones we'll see, TCP and so on, UDP, IP, and so on. But there are literally hundreds of other protocols within the TCP/IP suite. Not all are used to the same extent, obviously. Now, this diagram helps illustrate, a good overview of the protocols involved in the TCP/IP suite and the layer. Now, notice this is the TCP/IP model, not the OSI model, but it corresponds similar. It corresponds to the OSI model in a reasonable manner, right? So at the network access layer, we just have Ethernet or Wi-Fi and some other protocols, and then at that internet layer, what would be the equivalent of the network layer is IP. Most of our webinar also talks about IP version 4, right? That's still the dominant protocol being used in the world today and on the internet. So IP is the heart. And then we have TCP and UDP at the transport layer, ICMP also at the internet layer, and then all kinds of application protocols. Notice HTTP, HTTPS is what we use for surfing the web, and a lot of the other protocols are used for numerous applications. So what is IP? IP is the main protocol that's used to carry most of our data, right? So IP is the main protocol that's used to carry most of our data, and like I said, that's why I said it's at the heart of the protocol suite. In fact, the name TCP/IP comes partly from IP. It is routable. In other words, you can route the data. You can move the data from one network to another. If it's not routable, that means it's restricted to the same network only, right? So it's routable because of the address has a network and host portion in it. It's connectionless. That means two devices that are trying to exchange data using IP don't have to establish a logical connection with each other. They can just pretty much fire off. At the IP layer, protocol level, the data is just fired off as and when a device needs to send data. It's also unreliable. It means best effort. That means there's no acknowledgement. Whether the other side got the data or not, Well, I hope they did. It's pretty much IP's response, right? IP is not concerned with making sure like some protocols are. IP says, look, I tried. It didn't work. Oh, well, better luck next time. Is what IP says. And then addresses are 32 bits large, right? So 32-bit address. It is still, IP version 4 is still the predominant protocol used on the internet right now. Now, if you want to understand IP in a little bit more detail, how do you do that? Well, to do that, we'd have to understand what the header looks like. The details of the protocol are partly represented by the header. These are literally the fields in every IP packet. Every IP packet which we use, whether we, when we go to CNN or ESPN or we send email using TCP/IP, we go to shopping on Amazon, etc. All the packets we are exchanging for our data. When Amazon's website shows up on our browser, on our computer, it's carried in lots of IP packets, each of which has a header like this. So to understand the details of IP, we'd have to understand these fields. Now, I don't have time to go over them right now, but guess what? If you come to one of our classes, you'll learn specifically what these fields mean, and you'll see them in action in labs. Right? So that's the beauty of the IP protocol and all these details. Similarly, there's TCP. Right? TCP stands for Transmission Control Protocol, and I apologize. IP, of course, stands for Internet Protocol. Right? TCP stands for Transmission Control Protocol. TCP's properties, it is connection-oriented. That means that two endpoints, two devices that are trying to exchange data using TCP, before they can exchange any data, they have to establish a session. So it's connection-oriented, right? No data can be exchanged until this session is established first, and only then can they start exchanging data. It is full duplex, which means the two endpoints can send and receive simultaneously. Now, half means you can only do one at a time. Reliable, it is reliable. TCP is connection-oriented reliable, unlike IP. Reliable means it uses sequence and acknowledgement numbers. Data has to be acknowledged. If I send you something reliably, I'm going to expect an acknowledgement from you. And if you don't acknowledge it, guess what I'm going to do? I'm going to assume that you did not get it. I'm going to send you another copy. That's what TCP does. And obviously, all this is done with far more details, with a lot more complications. But that's essentially what will help us exchange data reliably. It also has sender and receiver side flow control. Now, flow control means speak faster or speak slowly, right? Or send data faster or send data more slowly. That's what flow control is. But each side can control that independently. For example, one of you might say, hey, Parag, slow down right now. Don't speak so fast. And I might say, okay, how's this? Right? So sort of like that. And another one of you might say, hey, Parag, not so slow. Just talk normal. All that's part of flow control. And the beauty is it's dynamic. It can be adjusted as and when needed. Right? So that's the beauty of TCP. One-to-one delivery. It's only between two endpoints. No party line, no group chat here. Only between two endpoints, one-to-one delivery, and uses port numbers to identify applications. I'll show you what that means in a moment. But, TCP can and is, in fact, used to carry data for multiple applications at the transport layer. Well, how will TCP distinguish which application this particular individual piece of data is meant for? And so that's identified by the port numbers, right? So, and this is what a TCP header looks like. So with TCP header, again, you have various fields, including the source port, destination port, sequence and acknowledgement numbers, etc. And to understand the protocol, we would have to understand the purpose of each field, its size, and how it works, right? What are the properties of these fields and how they are to be used. So that's, again, the details of learning about TCP as well. Like I said, in this context, I would take a half hour to explain some of the details of these fields and associated information in a typical class. So we can't go over these right now just because of lack of time. But at least it gives you an idea of what to look for and how to go about learning this. Should you want to learn this in more detail. Similarly, UDP is another core protocol. UDP is connectionless, unreliable. I like to use the term fire at will for connectionless. Whenever you're ready, just shoot, boom. Hope they're listening. Hope they get it. That's what connectionless means. Unreliable, sometimes is referred to by the term best effort, which is, by the way, in my opinion, highly misleading, right? If you say, Parag, can you do this for me? And if I say, I'm going to give it my best effort, and then I'll say, just like UDP, then you should be worried. In fact, you should have plan B already, because that means I'm going to barely try in this context, okay? Normally, best effort means I'll try pretty hard. But in this context, when it's unreliable, it actually literally means I'll barely try. That's what UDP does. It tries it once, and then if it doesn't make it to the other end, UDP says, oh, well, I don't know, I don't care whether it made it or not. That's UDP for us. Sometimes it's appropriate to use UDP. Sometimes it's appropriate to use TCP. So certain applications, the application decides, and again, it's not the application that decides randomly. The developers of the applications would have decided whether to use TCP or UDP. And when I say applications, I even mean the applications in TCP/IP, right? So the various applications in TCP/IP, like HTTP and DNS and Telnet and so on, they have been configured to use either TCP or UDP. UDP also, like TCP, uses port numbers to identify the application. And obviously, when a protocol is connectionless, no session established before exchanging data. When it's unreliable, no bothering to check for acknowledgments or whether the data made it or not, whether it was corrupt or not before, not before, but when it got to the other end. Then life is much simpler, much less overhead, right? Life gets complicated when you're trying to do more, trying to be more thorough, and so on. And of course, as a result of it being simpler, it's also faster. So UDP, that's one of the benefits of UDP. It is faster. And this was a bigger deal when networks were slow. These days, networks are very fast, right? So it's not as big a deal or as big a concern of a protocol being faster or slower. But that's the general idea. Also bear in mind, excuse me, I want to remind us that all this was developed almost half a century ago. So you know how you and I want to use the latest and greatest smartphone or laptop or a tablet? Well, guess what? We're using almost a half-century-old protocol with it. So it was not designed for our current networks, current bandwidth, current speed, and the current uses also. They didn't in their wildest dreams imagine that half the world would be downloading YouTube videos using this from a public network. This was originally designed for the U.S. Department of Defense, right? So that's why IPv6 is a long overdue upgrade for it, right? So this is what the UDP header looks like. Notice it's much, much simpler. By the way, this is the Ethernet header, the IP header, and here's the UDP header. Just 8 bytes. Versus, let me show you, TCP header. This is 20 bytes, guys, right? So I'm not showing you in this context. Notice the Ethernet header is 14 bytes. IP header is typically 20 bytes, but could, with options, be up to 60 bytes large. TCP header is the same way, 20 to 60 bytes, depending on options. UDP is 8 bytes only, fixed. No more, no less. Source port, destination port, link, checksum, and you're done. And the rest is actual data. So that's UDP for us. Other core protocols, right? Again, including a lot of the application protocols like DNS, HTTP, SMTP, FTP, Telnet, DHCP, SNMP, and so on, right? RTP, SIP, etc. So these are some, not all, of the other core protocols that we have. And so in order to understand TCP/IP, we'd have to know the workings, at least at a basic level, if not full details, of a lot of these other protocols. right? So that's the idea behind knowing even a lot of these protocols, because they are at the end of the day core protocols. Yeah. Now, one of the other big functions involved with moving data from point A to point B is routing. Routing can be thought of as moving data from one network to another. If you're trying to move data from one device to another device within the same network, you don't need to route. You just need to find the destination and send it to that particular destination because it's all in the same network. But routing involves moving the data from one network to another. Now, in this case, they're showing us 4 different networks, if you would, interconnected through a relatively complex wide area network with a whole bunch of links. What I also want to point out is that from any of these networks, there are at least 2 different ways to get to any other network. Sometimes 3, right? So from this LAN, there are 3 ways to get to the other networks. And from some of them, there's only 2 ways. For some of them, there are 3 ways to get there. And of course, in between, there are lots of different ways, right? So when I say 2 or 3, I mean at least that. It's actually a lot more. Different paths can be taken. And routing involves making that decision of which is the best way to forward data, towards the destination, which is the best path, in other words. And of course, the question is, what determines what is the best path? And the answer is there's certain criteria that will be used to figure out which is the best path, and the information, the best path information is usually stored in a routing table. Okay? Even though, by the way, notice each of these routers knows about multiple ways to get to various destinations, only the best path information is stored in the routing table. So the routing decision process involves checking a packet's destination address against the routing table. Now, when that is done, there are 3 possibilities. One possibility is that only one route matches, right? So individual routes in the routing table will match potentially the packet's destination. So only one route matches that particular destination, and that makes life easy for the router. And so yeah, just select the route, forward that packet to using that route, and you're done with that packet. Of course, routers are dealing with millions of packets per second potentially, so all this has to be done super fast. But another option is no routes. If a router has no routes for a particular destination, then that packet is discarded. The route and it's reported as destination unreachable. A router literally throws away the packet, says, sorry, I don't know how to get there. And then it sends a message back to the source saying your destination was unreachable. Sorry. The third possibility is there are multiple routes matching that packet's destination address. Then the longest bit match is used. It uses the most specific or the best match based on the longest bit match. In other words, maximum bits matching between that route, between these routes and the packet's destination address. And if still there are multiple matches, then the lowest metric is used. Metric, by the way, is nothing but the measure or unit of how easy to reach or hard to reach a destination network is. Yeah? So there can be lots of different types of metrics. Hop count is a very basic, very elementary and crude almost metric. It's just measuring hops. It does not take into account the distance, the bandwidth, or anything else. So hop count was one of the earlier metrics used in the more basic routing protocols. But today, the more sophisticated or advanced routing protocols would not use hop count because it's too limiting. Right? It's too constrained, if you would. Bandwidth is a more sophisticated metric, if you would. It allows us to make more intelligent decisions that are more relevant, more representative of how hard to reach or easy to reach a destination is. And you can even arbitrarily designate a cost associated for a metric associated with each link. For example, in each of these links, you can have a cost assigned to each of these links, and then the routers will say, oh yeah, the cost to get to this destination through this path is 50, versus the cost going through this path would be 100. So naturally, we'll prefer the lower cost path, and so that's how it could be done as well. But then the administrator has to specify the arbitrary path cost designation for each link, and so again, depending on how complex or simple the network topology is, that's feasible or not. There are other metrics which are not used as commonly, but reliability and delay can be used. Load even can be used. Now load might seem attractive, but it's not as a metric. So just keep that in mind. There's a little bit more to the details, but I don't want to get into it right now. But the bottom line is, usually bandwidth is one of the more commonly used metrics these days. And by the way, different routing protocols use different metrics, right? So, and that partly determines how they work, how sophisticated these protocols are, and so on. Routing protocol, again, operations, right? They figure out the best path based on different criteria, depending on what metric is used. So a protocol that uses hops as its metric will think the bottom path is the best path between lands A and B, right? Because it only involves 2 hops, 1 and 2, and you'll get there. Whereas the routing protocol that uses hops as its metrics might think that this gigabit path, 1, 2, 3, 4 hops, is far inferior to the 10 megabit per second path that uses only 2 hops, and so on. So that's how you want to think about some of these routing protocol ideas. Right? So if the question was, what's the best data path from LAN A to LAN B? The answer is it depends on the routing protocol between RIP, OSPF, ERP, and BGP. Different protocols will use different paths depending on what they consider to be their metric. Right? So like I said, RIP, by the way, instantly uses hops, so it would prefer the bottom path, which is far inferior to the gigabit path. Yeah. All right. So, by the way, here are the applications, and here are the respective port numbers, and here are the transport protocols they use. So these applications use TCP, these applications use UDP, and DNS uses both. It's not either or, it uses both. For some DNS functions, it uses TCP. For some DNS functions, it uses UDP. But these port numbers will uniquely identify for the transport layers which application or process to send the data to within a device. Right? So that's the idea behind these application protocols. Yeah. Now, yeah, and again, all of these headers will have some information on the next protocol up. So the IP header actually has a field called protocol, which will identify whether to send the data to TCP or to send the data to UDP or to send the data to ICMP or even one of these other routing protocols. Then in the transport, in the TCP and UDP header, we had source and destination port numbers, which would be these, which will help identify which application to send the data to. Similarly, by the way, Ethernet Wi-Fi headers have a field in there that indicates whether to send it to IP version 4, or if you happen to be running IP version 6 simultaneously, whether to send it to that, or some other port protocol also. In the past, by the way, there were a lot of other protocols out there. In fact, IP was not as popular. So in the earlier days of my career, I've also supported non-IP protocols in networks. Right? So literally, the Ethernet header would have information on which protocol to send the data to, and so on. Right? Now, IP addresses themselves are to be understood, and there's a lot to it. Now, so what you and I write as in a dotted decimal format, right, like 172.16.200.1, is actually a 32-bit string. It's literally a 32-bit long number with just 32 ones and zeros. You and I can't deal with that very easily. If I asked you what's the IP address of the device here and you start giving it to me in binary, I would say stop. before you get too far, because I can't process 32 bits in my head or even on paper very quickly. So that's why we converted to this dotted decimal notation, which has a network ID or a prefix as it's called, and a host ID, or what is sometimes called locally administered ID. So it has a network and a host portion is how I like to commonly refer to it. And every device, whether it's a router interface or whether it's a PC, whether it's a tablet, whether it's a server, whether it's a printer or a switch, all devices have unique IP addresses, right, to uniquely identify that specific interface. So that's the idea. So this is what an IP address might look like in binary, but we break it up into 4 octets, as it's called, 4 octets. In other words, 4 blocks of 8 bits each. We convert each block to decimal. We separate them by periods, and it becomes a dotted decimal notation. Now, so that's the idea behind the dotted decimal notation of IP address. So that's why if you give me an IP address like it in this format, I'll complain. But if you say it like this, I'll say thank you. So that's the idea. Now, at the end of the day, these IP addresses have to be subnetted these days, or not. I shouldn't say these days like it's new. We've been doing it forever. But the point is, we still need to know about subnetting to really understand how these addresses work. So when they first, developed TCP/IP, it was meant for the DoD, U.S. Department of Defense only, right? Then it was made available for other organizations, and eventually it became available for the public. So as that happened, they quickly realized, okay, we are going to run out of addresses very soon, because everyone in the world needed IP addresses, and there weren't enough to go around. There still aren't with IP version 4. We've officially run out of IP addresses by and large in IP version. But the goal was to make networks more manageable and to reduce address waste. So we had a network and a host portion. Originally, a third tier was added, and that was called the subnet portion. So the question to determine the properties of the third tier, we'd have to ask ourselves, how many broadcast domains or how many subnets will we need? How many IP addresses will we need? How many host addresses will we need? What is the total range of the addresses? And what is the potential for growth? Will the number of subnets grow, or will the number of hosts grow in a given organization, or both? Depending on that, we will want to leave some flexibility in the appropriate portion. Now, before we can understand subnetting, by the way, just so you know, when I teach subnetting in our classes, it takes me literally at least 4 hours to teach it. Why? Because I don't teach subnetting without teaching all these other things. So I literally teach all these other things before I do any subnetting. The first thing is, of course, why do we need to do subnetting, right? What is the purpose behind it? And that's answered by some of these points here. Then we need to understand the binary numbering system, how the binary numbers work, and how to convert binary and decimal numbers to each other. So that's the next thing you need to know. I mean, I could potentially teach you some formulas and shortcuts, but guess what? If you don't know what you're doing, you could easily be fooled or get confused. If with just formulas and shortcuts. But if you know all of this, I can't possibly confuse you. Not just me, but any problem. So that's the reason to know all these things, right? And then the IP address classes and their octet boundaries, right? In other words, octet boundaries refers to how many octets are network, how many octets are the host portion. And then, so that's the IP address classes, A, B, and C primarily. And the octet boundaries, subnet masks have to be known, along with the rules. Subnet mask is typically accompanied along with the IP address. And so we need to understand what it is, how it works, the rules, and so on. We also have to be able to figure out the number of bits and number of host table. In other words, if we have a certain number of bits for the subnet portion, certain number of bits for the host portion, how many hosts or subnets or hosts will that result in? Right? Or another way to think of that is if we need a certain number of hosts or subnets, how many subnet or host bits will we need? So that will also require us to have the ability to count the bits in an address and also be familiar with the prefix notation, the /16, /24, etc. Now, subnetting, I like to think of as a pizza, right? Or not subnetting itself, but I like to think of our network as a pizza, and the unsubnetted network, the entire original network, is the entire pizza, and a slice is but one of the subnets. So when we slice the pizza, we are creating subnets, is how I like to look at it. The address of the unsliced pizza, the entire address is a network address, 172.16.00/16, for example, before subnetting. The address of the slice after subnetting could be 172.16.5.0/24. And again, all this will make more sense if you understood all these basics really well. And that's why it takes me so long to teach subnetting, because I explain all these basics before we can continue, right? Or before we can understand subnetting. And I don't do any subnetting, any math, until all this is explained at least once. And students have had a chance to digest some of it and review it. Now, IP version 6, of course, is a long overdue upgrade, and has been around. IP version 6 has been around forever as well. We just haven't, many of our organizations haven't migrated to IP version 6 yet. So what are some of the big features? Well, IP version 4 addresses were 32 bits large. IP version 6 addresses are 128 bits long. 4 times as long, guys. Now, think about that, which means we will have a gazillion addresses. We are not going to run out of IPv6 addresses, even if we assign an IP address to every carpet tack, every nail in the house, every nail for the carpet or carpet tack, not to mention all the gadgets and gizmos, right, for a thermostat and TV and light bulbs and wall jacks, not to mention all the PCs and cell phones and tablets, printers, a refrigerator, dishwasher, clothes washer, you name it. We can assign IP addresses to all of those and still never run out of IPv6 addresses. That's how huge it is, the address space. And that's why they made it so big, right? So it also has numerous other features. So one of the big things is it actually has simplified the header. So remember I showed you the IPv4 header? It had quite a number of fields. They have actually reduced the number of fields in the IPv6 header. So you might say, gee, that means they reduced some of the functionality. And the answer is no. They removed some of the functionality from the basic header, but they added it as extensions and option headers. So we have extended option headers, right, and all kinds of extensions, like for authentication, encryption, things of that sort. And we have these extensions and options, so option encoding and extended option headers for all that functionality and more. So the benefit was that not all devices need to deal with a more complex header. They can deal with a much simpler header, but as needed, they can deal with whatever extended option header they need to. Right? So that's the idea behind IPv6. They also addressed they assigned, not addressed, but they have assigned IP addresses based on regions. So regional cluster addressing. With IP version 4, addresses were assigned almost randomly, and so not sequentially. Whereas with IPv6, the addresses are assigned based on regions. So just from the address, we'll be able to tell what region it belongs to. Right now, it's much harder to do. It's not as easy to do that. It is possible, but much harder to do. Now it's much more simplified. They have also added, they've added the capability of auto configuration, the capability of built-in security. Right? So IPv6 has better security built in. IP version 4 did not. So encryption extension is one of the key ideas there, right? And quality of service is maintained. IP version 4 had it. IP version 6 still has it. And what else? So authentication extensions added. It's easier to auto-configure IPv6, and a bunch of other benefits are added. But one of the big things is IPsec, IP security, was developed as part of IPv6, and it was ported to IP version 4 as an option. Whereas with IPv6, it's an integral part of the protocol. So that makes it a lot more secure from that standpoint too, natively built in. Right? The quality of service, like I said, has been maintained as well. And source domain route support is also maintained. We had that on IP version 4. IP version 6 still maintains it. And auto configuration makes it easier to obtain the IP address automatically. And then transition plan. Now, here's the thing. Fundamentally, IP version 4 and IP version 6 are two different languages. Even though they both have the term IP in them, they are two different protocols, different address sizes, different headers. They are not compatible. A device using IP version 4 cannot talk directly with a device using IP version 6. They have to have some translator in between. Right? So that's the idea behind IP version 6. And that's partly what has made the transition to IP version 6 so slow, because it's quite involved. Now, there are some tools and mechanisms to help ease the transition pain to transition to IPv6, to help with incremental migration, right? Such as, capability to talk both IP version 4 and IP version 6 simultaneously, called dual stack. They provided tunneling, NAT, and so on. So there are numerous options to help transition, so you don't have to cut over abruptly the entire network overnight from IP version 4 to version 6. You can do it incrementally or slowly, right? In phases, in regions, and so on. Bottom line, IP version 6, long overdue upgrade, and has lots of benefits. It's also got a much longer address, definitely a little bit more complicated overall as a protocol, but far greater capabilities and some simplification as well. So quite nice in a lot of ways. Now, that's the basics of what all you would learn or you should know as far as TCP/IP goes. And again, in more detail than obviously I'm able to cover in this short webinar, right? So here's some something to tickle your funny bone after bombarding you with 35 minutes of a little bit of intense information. Take a look. I won't read these out loud. See what you think. Feel free to make some comments or see what you think. All right. So now, if you guys have questions, feel free to put it in the Q&A box.
Thank you so much. Fantastic. I'll get these questions in just a moment. Everyone, I'd like to thanks everyone for your questions and your engagement, and thank you, Parag, for the fantastic presentation. I don't know if a lot of people know this, but our presenters generally do this kind of on their lunch break while they're teaching. So we really appreciate you giving up your lunch. You will be getting a copy of this recording in about a week. It will be sent to the email that you provided when you registered. So let's get started here with these questions. So first, can you explain ARP protocol with examples?
Sure. Let me take a brief stab at it. I'm going to go back to one of the earliest slides to help do that. And here's the deal. So at the end of the day, when I type in www.amazon.com, my PC has to put Amazon.com's IP address in the destination field and my own IP address in the source field of the IP packet. That IP packet, though, is going to be wrapped into an Ethernet or Wi-Fi frame, depending on what I'm using in my network. For that, it has its own source and destination addresses, but these are MAC addresses. Now, source MAC address would be my own. Again, my device would know it, no big deal. But the destination MAC would have to come. I would have to figure out what the destination device's MAC address is. And it would not be Amazon.com's web server's MAC address. It would be my local router's MAC address. But to determine that, an ARP request is sent out. ARP query or an ARP request is sent out saying, hey, such and such IP address, what's your MAC address? And a response comes back to my machine only. The request goes out as a broadcast because I don't know who to send it to. But the response comes back just to me or my device as a unicast, telling me that device says, oh yeah, that's my IP address, here's my MAC address. And once I receive it, that's an ARP response. I will put it in an ARP table or ARP cache as it's called, right? Same thing. And then I can use that information next time I need to speak with that device. Basically, is how ARP would work, right? So that's specifically it. I hope that answers your question.
Fantastic. Let's
yeah.
move on to the next one here. Is IP version 6 more secure than IP version 4 as cybersecurity is concerned? And that's from Bad Boy, Bad Boys for Life.
Huh. Okay. Yeah. IP version 6 has IPsec, IP security built in. It was integrated and designed for IP version 6. In fact, it was so good that they said, well, look, this is really a great enhancement for IP. And who knows when the human, when people will migrate from IP version 4 to version 6. So let's port this IP security, IPsec to IP version 4 also. So it was actually ported as an extension or as a FluGI add-on for IPv4. It's a native or integrated component of IPv6. Therefore, inherently, it makes it more secure. And there are a few other security mechanisms as well. Yeah? Good question. Thanks.
That was a great question. Thanks. So good afternoon. I have a question regarding the definition and examples of TCP slow start, since I encountered the term whilst attending a class earlier today.
Oh, wow. Okay. So TCP slow start is a congestion management mechanism. And I don't want to get into it in more detail right now just because it would be a little inappropriate to get into it in more detail. But the idea is that anytime TCP encounters congestion, either because some packets were dropped, or as a symptom of that would be some packets are dropped, or there's a delay in acknowledgments or whatnot, it starts trying to deal with that congestion. And TCP slow start is one of the basic mechanisms that's included with TCP. TCP also has a bunch of exotic mechanisms, the very fancy ones to deal with congestion, but slow start is one of them. Yeah. And again, it has to do with how devices will then scale back, how they'll slow down the rate at which they send data so the other side can manage and cope with that. And the congestion could be either in the network or it could be in the destination device. Either way, the point is that TCP slow start will help ease the situation where congestion is involved. Yeah, so that's what it is. Thank you. Good question.
Fantastic. How are the different routes elevated in order to choose the best one? Meaning, in order to assign a cost to a path, its metrics have to be known.
Okay, good question. So the question is, how are the different routes evaluated, right? Yeah. So in order to choose the best one. So again, if I tell you what's the best way for me to get from Washington, D.C. to New York? Well, so the question would be, what do you consider best? Do you want the fastest path? Do you want the shortest path? Do you want to drive the least distance, or do you want to get there fastest? Do you want to pay the least tolls? Do you want the most scenic route, right? Do you want the least congested route? So really, the best route, the routing protocol defines what they mean by best, and usually it's based on the metric. So RIP would use literally, as I showed in an earlier slide. Let me go back to it. The RIP protocol would use a metric like hops. Yeah, OSPF And EIGRP will use bandwidth as the best as the metric to determine the best path. And so, they would choose the 1 gigabit link or the 1 gigabit path, right? So with the one, sorry, let me rephrase. They would use the path with the 1 gigabit per second links because they're valuing bandwidth as the criteria. And 1 gigabit is 1,000 megabits, which will beat 10 and 155, 155 megabits any day, right? So that's why this path is preferred. So going back, let me double check the question. Yeah. So and in order to assign a cost, its metrics have to be known. Yeah. So the routing protocols, the routers know what the metrics are. The routing protocols know what the metrics are, right? And they know the metrics for each link also that are connected to themselves at least. And they learn about the metrics for the path from their neighbors. So for example, the router on the left will learn about the metric of the path from the router on the right, which will know the metric of the path from the other router it's connected to, and so on. So they share all this information, and they exchange. That's, by the way, that is the entire purpose of a routing protocol, to share this information, to learn the details. And then the router will use the data you obtained from the routing protocol to make a decision on which is the best path. Right? So it will calculate all that. Right? So good question. I hope that helps answer that as well. And we, of course, I could go on talking about this for a few hours, like just the answer to that question, literally, because that's how detailed it can get.
Sure, and that kind of brings up another question here. How can students benefit from taking this class?
Well, so we'll talk specifically about one class that matches the contents of this webinar really well. It's called TCP/IP Fundamentals, right? Yeah, TCP/IP Foundation Knowledge. And the beauty of that class is, we actually talk about the details of the headers. We talk a little bit more details about concepts like routing. When I teach the class, I literally spend at least 4 hours teaching subnetting in that class. So you learn all these details and all the prerequisite knowledge for subnetting, right? Not to mention the fact that we actually go through labs in class, during class hours, in that class, because the content is not so condensed that we don't have time. And so we've specifically designated time to do labs in class under adult supervision, like mine, the instructors. And you get your questions answered. You see how these ideas and concepts and theories and these principles work in real life, in a real network, right? Even though it will be somewhat small scale, right? We're not going to give you access to Microsoft's enterprise network for that purpose, but we don't need to. For the basic principles, a small, simple network will get the job done. You'll see it live in action, and that really consolidates the knowledge with the practical aspect of it as well, and helps you learn in what my opinion, in a fantastic way. Just an FYI, in my earlier days of my career, I had taken more than 20 years ago, by the way, maybe more than 25 years ago, I'd taken a semester-long class on TCP/IP in a college. Back then, it was like very rare. It was the second time it was offered in that particular community college where I took it. And I tell you, I today feel students learn more in a 5-day class that we teach than I did in a semester-long class back then, because we didn't have labs. It wasn't explained. Professor was really good, but they didn't make that connection between the theory and the practice. Here we do that. We help you see the demo of how this works, not just demo, sorry, how it works in a live lab with labs, and we ask great questions in the labs which you have to answer, and that helps you learn as well. And of course, you get all your doubts cleared by a live instructor who's present during your labs and during lecture, and helps explain all these labs. I review the labs after the lab is done. So I think overall the learning, I feel, is fantastic. So yeah, that's my answer.
Awesome. All right, so we've got a few more questions here, and every time we do this webinar, we always have so many great questions. How does OSPF apply when talking about routing the best path?
Okay, so the question, I'm not 100% clear if I follow the question specifically, but I'll try to answer to the best I can. I mean, so again, in one of the routing classes I used to teach Cisco courses, and one of them was routing. I would spend literally more than a day on OSPF. Okay, and OSPF stands for Open Shortest Path First, right? The routing protocol OSPF uses the metric of cost, but that cost is based on bandwidth. So OSPF does make fairly accurate decisions based on bandwidth. And what happens is every router, if these routers were talking OSPF with their neighbors, each of the routers would have a full detailed map of this entire topology. They'd know which router was connected to which other router via what links, and they would therefore know the bandwidth of each link, and they would know the metric, the OSPF cost of each link. And each router can calculate the path cost from any point of the network to any other point. So even this router on the top can figure out the cost of other routers' paths to other destinations. So it's like, imagine having a full detailed map. Not only do I know how to get from my house to yours, but I know what any two of you, what path any two of you would have to take to get to each other's house, completely unrelated to mine. So that's how OSPF works, and it figures it all out. But it needs more memory and more processing power than some of the other routing protocols, like RIP especially. But it's very smart, very sophisticated, and very quick. And it's accurate. So it's hard to fool OSPF into loops or other problems also. Hope that helps.
Awesome. So we have two more questions here, and we'll let you scarf down your lunch real quick. What are private IP addresses and how to find it?
Very good. So, private IP addresses are specifically designated and reserved for use in our private networks. That means we cannot use those addresses to get to the internet, right? We can only use those in our internal networks. But of course, all of us want to be able to get to the internet. And the reason private addresses were reserved or designated is because we were running out of IP addresses. They knew that, okay, we'll run out of these pretty soon, so better save some for everyone to use in their internal networks. And the way to find it is just Google it. You'll find it. But then private addresses are then translated. By the way, your and my Wi-Fi router, our broadband router, Wi-Fi router, even the $30 Wi-Fi router that we buy brand new from the local stores, Walmart or Best Buy, has NAT capabilities, network address translation, where it will translate the private IP address to a public address so that our packets can go to the internet. And while we are still using a private address originally, it'll change the address to something that's allowed on the internet and figure out how to then change it back before it sends the data, the response back to us. So that's the general idea behind private IP addresses. It's great. It's really good question, and the beauty is it works like magic, and it allows us to use private addresses and still get to the internet. Good. Okay. All right. So I'll see the next question. I'll go ahead and read that. When we ping two websites and we get the same IP, what does it mean? When we ping two websites and get the same IP, now two websites should not have the same IP. Yeah, generally what it means is that some device in between that's acting as some kind of a proxy or intermediary or whatnot, right? So generally that would not be the case. Those are not the addresses of the website. It would be some kind of a proxy or some other device that's basically responding in place of that. Yeah, that's what I would say. It would be, yep, some kind of device in the interim. All right, Brent, you there? Just checking.
Yes, I am here. So I see we still have questions coming in, but in the interest of respecting everyone's time, we're going to go ahead and wrap it up here. But I will say this: if you have questions, if you have concerns or things you want to know, pretty please reach out to our social media team at Global Knowledge, Twitter, Facebook, LinkedIn, whatever platform you're on. Let's make this folks earn their money, and they can connect you with the right people to answer your questions. And so again, thank you, Parag, for your time today. I mean, absolutely fantastic as always. We appreciate you taking the time to do this for us. Thank you to everyone that attended today. I mean, your questions were amazing. Engagement's fantastic. It just makes doing these so much more fun. Obviously, the next class we would suggest for you is TCP/IP networking. If you'll see, you can put in the following codes to get 25% off with your next course at Global Knowledge. We want to make it nice and easy for you guys to get your training, save you a little cash money there. And please, continue to check back globalknowledge.com for additional resources, obviously webinars, but also white papers, articles, lots of good stuff. So again, we thank everyone for being here today. Parag, thank you again for your fantastic presentation and taking the time to answer everyone's questions. That's greatly appreciated.
Thank you, Brent. I'm sorry
absolutely.
to interrupt. Thanks a lot. And by the way, thanks all the participants. Thank you all for attending the webinar. Thanks for your great questions. Like I said, I feel bad sometimes even doing these webinars sometimes just because I have to limit how much information I can share just because of time. But in class, that's what the other benefit. When you come to class, most instructors like myself will be happy to even have discussions offline and answer your questions, resolve your difficulties, help you with your practical problems at work. And thanks a lot, Brent, for moderating this webinar.
Absolutely, my pleasure. And I saw a couple questions come through. Again, you will receive a copy, a recording of this presentation in about a week. It'll be sent to the email that you registered with. So again, thank you, Parag. Thank you, everyone. Enjoy your day. Stay safe. We'll see you next time.